So this is the last lesson of Unit 4, so Lesson 5. And in this lesson we're going to talk about two theorems. One is Rolle's theorem and the other is the mean value theorem. So the Rolle's theorem says if we assume, or to assume that f is continuous on the closed interval a to b and also differentiable on the open interval a to b, if f of a equals f of b, then there exists at least one number c in the interval a to b such that f prime of c, the derivative at c, equals 0. So if we take a look at this graph, so here we have x equals a, x equals b. If we take a look at the point on the graph, you'll notice that both of these points have the same y value. So that means f of a equals f of b. So when f of a equals f of b, this theorem says that there will exist at least one number c on this interval, so one x value of c, such that the derivative of this function at c will equal 0. So if you look at the graph, this point right here, the slope of the tangent line is 0. Well, if the slope of the tangent line is 0, that means that the derivative is 0. So that's what this theorem is all about. So let's take a look at an example, and I'm going to pull this sheet away as you guys follow along. But we have an example. I'm going to scoot this over a little. F of x equals x to the fourth minus 2x squared on the interval from -2 to 2. Okay, so it says the directions say determine whether Rolle's theorem can be applied to this function f on the indicated interval. If Rolle's theorem can be applied, then find the value of c such that f prime of c is equal to 0. So the first part of this, we have to determine if Rolle's theorem can be applied. So what that means is we need to evaluate the function at each endpoint. So I'll start with f of -2, and if I substitute -2 and raise it to the fourth, minus 2 times -2 and raise that to the second, pardon me, we get -2 to the fourth is 16, -2 squared is 4 times this 2 is 8, 16 minus 8 is going to be 8. Okay, now we want to evaluate the function at 2. And when we do, 2 to the fourth minus 2 times 2 squared, 2 to the fourth will give us 16. 2 squared times 2 gives us 8. And when you subtract, you get 8. So can Rolle's theorem be applied? And the answer is yes. Rolle's theorem can be applied to f because f of -2 equals f of 2, which they both equal 8. Excuse me. So there's the reason we tested to see if Rolle's theorem could be applied, and we found that the answer is yes. So now what do we do to actually find the x value that is on this interval where the derivative would equal 0? So we need to find the derivative. So finding the derivative of this function, f prime of x equals 4x cubed minus 4x, pardon me, and I'm going to set this equal to 0. So this is going to be f prime of c. I'm going to replace x with c. So it's 4c cubed minus 4c equals 0. These two terms have a 4c that is common. So 4c times, that leaves me with c squared minus 1 equals 0. If I set each factor equal to 0, the 4c gives me a value of 0, and c squared minus 1 equals 0. Oops, that should be c squared equals 1. So c will equal positive and negative 1. So, what do these values mean? Well, Rolle's theorem guarantees that if f of negative 2 equals f of 2, meaning the endpoints, then the theorem guarantees, keyword, at least one value of c such that f of c equals 0. So here we took our derivative, we replaced our x's with c's, set this equal to 0, we solved it, and we actually found 3 values such that f prime of c would be equal to 0. So c equals 0, 1, and negative 1. Now let's think about what that means. If you think about what this graph looks like, x to the 4th minus 2x squared, we know that that is a 4th degree function. We have our critical values, and if I were to do a little sign chart, negative 1, 0, and 1, then anything less for the derivative, anything less than negative 1, if I go here, this term is negative. If I take negative 2 and square it, that gives me positive 4. So this is negative times positive. So this will be negative. From negative 1 to 0, let's try negative 1/2. So negative 1/2 for this value of c makes this term negative. A negative 1/2 squared is positive 1/4. When you subtract the 1, you get negative. So negative times negative is positive. And then if we continue that process, we'll see that my sign chart reveals this information here. So if we put this in perspective, we know that we're going to have the original function will have a minimum, a local minimum at negative 1, a local maximum at 0, and we know that we will have, this function will have another local or relative minimum at 1. So, and we know, oops, I'm so sorry. Nope, there we go. So, at negative 1, 0, and 1, we know we're going to have this is a 4th degree function. We know it's going to start up, it's going to have that W shape. So, we're going to have a graph that's going to look something like this. Not perfect, but it'll look something like that. So when you look at this graph of this function, notice that there are 3 places, there are 3 values between negative 2 and 2 where the derivative equals 0. And that's what Rolle's theorem guarantees. Now we won't always have 3. We won't always have more than 1. Sometimes we'll just have 1. So, looking at, I'm going to pull this back into the picture. The next example says, explain why Rolle's theorem does not apply to this function even though there exists an a and a b such that f of a equals f of b. So when we look at this, we have this graph from A to B. F is continuous. But let's talk about, where am I? Let's talk about the differentiable piece. So I'm going to slide this back up to the graph. And And I want you to look at this point right here. This point at C, this function is not differentiable at C because this is a corner. Remember how if a graph has a corner in it, the function is not differentiable? And again, the way you could look at that is the slopes of the tangent lines from the left are positive and the slopes from the right are negative. So the slopes of the tangent lines at x equals c are not the same, which means the derivative does not exist. So even though f of a and f of b both equal 0, Rolle's theorem cannot be applied because this function is not differentiable at c. Okay? All right, so now let's move on and talk about the mean value theorem. So the mean value theorem connects the average rate of change of a function with the instantaneous rate of change of the function at a point within the interval. So if we take a look at this graph, the mean value theorem says that if y equals f of x is continuous at every point on the closed interval from a to b, and also differentiable at every point of its interval a to b, then there was at least one point c in the interval a to b at which the derivative at c equals f of b minus f of a over b minus a. So folks, really what this means is that there is going to be a value where the instantaneous rate of change is equal to the average rate of change. So looking at the graph that I have here, here's this graph in red. That's our function. Notice that the point from A to B, that's the slope of the secant line. That's the average rate of change. And there's a point on this graph where the slope of the tangent line and the slope of the secant line are the same. And that's what this mean value theorem guarantees. The function, this red function, has to be continuous and also differentiable at every point on the interval. So let's put this in perspective. Let's say that you're traveling in a car that is accelerating from 0 and takes 8 seconds to go to 352 feet. Its average velocity for the 8-second interval is about 352 per 8 feet per second, or that reduces to 44 feet per second, which is about 30 miles per hour. So at some point during this 8 seconds, the mean value theorem says that the speedometer must read exactly 30 miles per hour. And so that's a really good illustration for this idea of the mean value theorem. So if your average rate of change is 30 miles per hour, then some point along the way in your travels over that 8 seconds, your speedometer had to read 30 miles per hour. Okay, so let's put this into practice. I'm going to pull this away. And our example says to show that f of x equals x squared satisfies the mean value theorem on the interval 0 to 2. Okay, pardon me. So the mean value theorem, we know we want to find where f prime of c equals f of b minus f of a over b minus a. Remember, this is the instantaneous rate of change equals the average rate of change. All right, so what is f prime of c? Well, that's the derivative of 2x, which I can write it as 2c. F of b, now f of b, f of 2 equals 2 squared, which is 4, and f of 0 is 0 squared, which is 0. So I'm going to take the 2c and I'm going to set it equal to f of 2 minus f of 0 over 2 minus 0. F of 2 is 4. F of 0 is 0. We divide that by 2 minus 0. And we get 4 over 2, which is 2. 2c equals 2, so c equals 1. Okay, so mean value theorem says that if this function is continuous and differentiable on the interval 0 to 2, let's take a look at let's put that in perspective of to what we know that to look like. So that's a quadratic. We know it opens up. We're only interested in focusing on the interval from 0 to 2. So this portion right here. Okay, so the average rate of change, the slope of that secant line, we found to be 2. And what the mean value theorem says is that there will be at least one x value on this interval 0 to 2 where the derivative equals the average rate of change, which is 2. So the c value that we found is at 1. So at 1, there's a point on this graph, kind of hard to see, where the tangent line and the secant line have the same slope. So that point is at c equals 1 or x equals 1. Okay, then let's look at the next example, and this will close out this lesson. So our next example, we are given f of x equals 5 minus 4 over x. And we want to find all values of c in the open interval 1 to 4 such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. Come here. Sorry for the pause. So we want to find all values of c. Alright, so the first thing we're going to do is let's find f of 4. Or first of all, let's think about this. This function is going to be, we can assume that this is a continuous and differentiable function on the interval 1 to 4. So we need f of 4, which is going to be 5 minus 4 over 4, which is 4, because 4 over 4 is 1. F of 1 will be 5 minus 4 over 1, so that turns out to be 1. For the derivative, I want to rewrite 5 minus 4 over x as f of x equals 5 minus 4x to the negative 1. It'll make it a little easier to find the derivative. So the derivative of this, the derivative of 5 is 0. The derivative of negative 4x to the negative 1 will be 4x to the negative 2 equals f of 4 was 4 minus f of 1, which was 1, over 4 minus 1. Well, that's going to be 3 over 3, which turns out to be 1. So I have 4x to the negative 2 equals 1. Now, I guess I should be using c's here. I'm going to rewrite this expression right here where the exponent is positive, and I'm also going to put the c in there instead. So it's 4 over c squared equals 1. So what can we do now to solve this for c? Well, cross multiply, and we get c squared equals 4, c equals plus or minus 2. So it appears that there are two values where f prime of c equals f of 4 minus f of 1 over 4 minus 1. In other words, they're at 2 and negative 2. The derivative of the slope of the tangent line will be the same as the average rate of change, which was 1. But there is one thing, and I'm wondering if anybody has caught it. Mathematically, we found 2 values for C, 2 and negative 2. But the interval that we're focusing on is only from 1 to 4. So to answer this question, it says find all values of C on the open interval 1 to 4. C equals 2, the positive 2, is the only value that is on that interval. So, so that is utilizing the mean value theorem. So that wraps up lesson 5. As always, sorry about that. Let me encourage you to reach out if you have any questions or need any help with any of this. I will be available for questions or to answer any of your questions that you may have. All right, till next time. See ya.